OK. Bonjour, merci d'être venu. Welcome. Thank you for coming. Any questions from last time? Okay. So, last time we defined the Matsubara Green function in imaginary time. So we defined G of R prime, and tau as minus the time-ordered product. So in French, it's the produit chronologique. And it's time ordering operator. In French is l'opérateur d'ordonnancement. So si tau, no, sorry. Psi of R and tau, psi dagger of R prime times 0, or depends only on the time difference. Okay, so the time ordering operator puts operator that have a larger imaginary time to the left. And we saw the time evolution operator of this. So today I will go to frequencies here, and then use the Lehmann representation to show that this is easily related to the retarded Green's function that we saw as physical meaning. And so we will define a generalized Green's function everywhere in the complex plane that reduces to the retarded function when it's on the real axis or infinitesimally close to the real axis, and to the Matsubara Green's function otherwise. Then I'll do the example of a translationally invariant system, and then non-interacting system. So and then we will learn to do some sums of these Matsubara frequencies, because we will often encounter this. So the first thing is we said that to go to a frequency, we will use the fact that the Green's function has the property, for example, of G. And now just to shorten this notation, I use alpha. Oops, sorry. Pen already running out. G alpha beta of tau, let's say tau is less than 0, is equal to minus G alpha beta of tau plus beta. So I shift for beta, and then I flip the sign. Okay, so then if I periodically extend this thing, okay, I need it only on the interval minus beta to beta. So if I periodically extend this, I can use Fourier series. And if I use a Fourier series, then you find out that you can write that G alpha beta of tau is equal to 1 over beta times the sum over n equals minus infinity to infinity of e to the minus I. I will define kn in a moment, tau times G of ikm. And I still have place here. Okay, so ikm, or kn, let's say, is equal to 2n plus 1 times pi times the temperature. So it is an odd number of times pi. So if I put units back, I will return to the units that we use normally, where h bar equals to 1 and the Boltzmann constant is equal to 1. But if you put them back, it's like this, okay? So Kn is a frequency. And most of the books, actually, you will see that it's written omega n instead of Kn. But I prefer to do that because then it's easier to connect frequency to momentum. They are also called K. The difference is that the momentum has a vector sign, and Matsubara frequency has an index n. But they both call K. So that's why I do that. Okay. So now, why does this reproduce this property here? You see that if I add beta to this, suppose tau is negative and I add beta, what will happen? Here I will go to tau plus beta. And what happens to beta times Kn? So there's a temperature here. So beta cancels the temperature. So now I just have 2n plus 1 pi. So it's an odd number of times pi times I is a minus sign. Okay? So it does have this property. And if you look at Fourier series, the way to represent these functions is really like I did this. So it's really bachelor level. I mean, now what is the revert? Does it work again? Yes. So now if I want to know G alpha beta of IKN, then it's equal to the integral from 0 to beta of E to the, let's see, did I make a mistake here? Some over M. Yes, that's okay. So E to the I Kn tau times G alpha beta of tau d tau. Okay, so the integral from 0 to beta d tau G alpha beta E to the I Kn tau. So if you look again at the properties of Fourier series, you see that this is really the reverse of this. Okay, so the interval from 0 to beta is continuous, but it's in a finite interval, and we repeat. So the Fourier coefficients are discrete. So these are called the Fourier Matsubara frequencies. Okay, you have any questions? Okay, so again, just to have a short notation instead of these R prime and so on, I just use G alpha beta, and we will work out the spectral representation for this G of IKN. So what I want to do is to show that it has exactly this form here, but with Z equals IKN. Okay, that's the purpose. And then I will not do the calculation, I will let you check, because it's really easy, that the spectral weight for the retarded function is exactly the same as the one I'm going to find right now. Okay. So if you remember, for the retarded function, we had omega plus I eta. Now we will have IKN. So clearly the two functions are just related by analytic continuation. Okay. So let's see how we work out this quantity. So if I do the integral from 0 to beta d tau e to the I k n, and now I have g of the tau. So the time here, tau is larger than 0, which means that the destruction operator is the one that's appearing here. So there's a minus sign, and we have C alpha of tau, C dagger beta. Okay, that's all I need for the time ordering operator here, because the tau is larger than 0. Okay. Now I'm going to, we are going to write the expression for this. C alpha of tau, by definition, is e to the k tau, where k is h minus mu n, times the C alpha times e to the minus k tau. Okay, that was the definition of the time evolution, imaginary time evolution operator for this. So if I do this replacement here, I can rewrite this as minus integral from 0 to beta d tau e to the I k n tau. Okay, now there's a possible confusion, but I think the context will be clear. I sum over n m. So these will be energy, this will label energy eigenstates. Then I have 1 over z. So the sum over n is the trace here. So I have e to the minus kn times beta times n times e to the kn tau, because this operator acts on this, and I have C alpha e to the minus km tau, because it acts on this energy eigenstate, and I have running out of space. So let me write it just below here. So I have m C dagger beta m. So is it clear? I did a trace. So the trace is the sum over n, and the density matrix is e to the k beta. So that's e to the minus kn beta. And I put a complete set of states here in between, right there, sum over m. And then these operators act on this and on that. Okay? Is that okay? Yes? Okay. So all we have to do is this integral. So I'm left with sum over n m. I have a minus sign. I have 1 over z times e to the minus beta kn. That's it. And then I have tau, tau, tau. So I need to do this integral, but it's just an exponential, so it's easy to do. I get exponential of I kn tau. Kn, let me write it. Let me put everything together. Kn plus Kn minus Km tau. From 0 to beta divided by I Km. There is the I should be inside here. IKN minus Km minus Km. and then times this. So times n C alpha m m C dagger beta m. Okay? We just integrated an exponential, so not too complicated. Now, when I go to beta here, this will become beta. And we have already seen that beta times ikn gives -1. And when I go to the lower bound, I will also have a minus. So this minus is gone. And the upper bound is just then e to the kn minus km beta. And the lower bound, I had the exponent e to the 0 is 1, so I have plus 1. And now we are done. So when I combine all of this, I have, so the kn disappears here, but what's happening? Yes. So the kn disappears in this case, and I'm left just with the beta kn. And then I have this acting on this. Okay? So I have e to the minus beta km plus e to the minus beta km. Okay. Now you see that this I can write like this. I can write as equal to the integral d omega prime over 2 pi times exactly this, okay? A alpha beta, I will not write this. I mean, it's equal to this. No, okay. A alpha beta of omega prime divided by ikn minus omega prime. If I define this spectral weight, as long as I define A of alpha beta of omega to be equal to 2 pi times delta of omega minus k m minus k m times e to the minus beta k m plus e to the minus beta k n times n c alpha m m c dagger beta n.
So you forgot the sum and the 1 over z?
And I forgot the sum in the 1 over z. Excuse me. Okay. So if I have this delta function here, when I do this integral over omega prime, then I will get the sum over mn. The 2 pi will cancel out. And I get this plus this, and I get this. Okay, what will happen if you do the same, if you find the a of omega for the retarded function? So I will let you do this exercise. But you see, you remember that the retarded function was an anti-commutator. So that's why there's a plus sign here. And then there is just a change of m and n. Dummy indices in the two terms. There's one term and then there's another term. And then you just change the dummy indices and then it becomes like this.
Just to be sure,
Yes.
in the integral, in the second to last equation, in the denominator, I times kn,
Yes.
the same n that is in the sum that's now in A alpha beta?
Yeah, I knew that would cause problems. So this n is not the same as this n.
Oh, okay. Oh, yeah, you're
Okay,
right.
this n goes goes here,
Uh-huh.
and this is just a label for the k. So perhaps I should change all my n and m for some other variable, p and q. Okay. So, okay, so now you see that if the retarded function, okay, you can easily prove for yourself that the retarded function is exactly this with this spectral weight, except that here you have omega plus I eta. So you see that if I define this function like this, so this is the complex plane. So I have real part of z, imaginary part of z. So this function is defined along this axis. So the Matsubara frequencies are spaced just like this. And then the real part, the retarded part is a function that's defined infinitesimally close to the real axis. So it is this function evaluated at omega plus I eta. And the advanced function is defined at omega minus I eta. So if we do a calculation in Matsubara frequencies, we get the results at this point. And when we have observables, we want to find them on this point. Okay, before I do that, let me just mention one last thing here. You see that this I will connect what we just found with the photo emission, right? I told you that we computed a cross section for photo emission, and I told you it was related to the Green's function. So take this term here and rewrite it as e to the minus beta km times 1 plus exponential of beta omega. Okay, omega is this here. Omega is km minus kn. So when I replace omega by km minus, so km is this. And when I replace omega by km minus kn, I get rid of this and I'm left with km. Okay? So this can be written like this because of the delta function. Now, if you go back, well, even myself, I didn't remember all the details. But so if you go back to the cross section for photo emission, you will see that it is it is equal to the Fermi-Dirac function times A of K. So the index alpha and beta here will be momentum now, KK if you want, of omega. And the Fermi function, that's the inverse of the Fermi function. So the Fermi function times this gets rid of this term. And what's left of this product is exactly the proportional to the cross-section we found for photo emission. Okay. So the information on photo emission is either in the retarded or the advanced function, or the Matsubara function, doesn't matter. The information is in this spectral weight, which can always be extracted. Okay, now there's an ambiguity in here, which is the following. Suppose I know this Matsubara function of I know G of Z, and I multiply by e to the beta Z plus 1. Okay. Okay, this function is not G of Z. This function is G of Z plus this times G of Z. But now you see that when Z is equal to these points on the axis, this factor is 0. So this function takes exactly the same values at these Matsubara points as this function. So in other words, the analytic continuation is not unique. Knowing the function here does not determine it everywhere. Okay. But there's a theorem that says the following. If you analytically continue and you find a G of omega plus I eta, which is equal to G retarded of omega, that it is analytic in the upper half plane. And then if you find that G of IKN, so when you replace as exactly the the value this function G of Z, what symbol should I use here? Here I use a big G. Let me not confuse the things. Yeah, sorry, I was a little bit faster. So G. So G of IKN is equal to this G of Z equal IKN. Okay. So, but this function satisfies this. Okay. Now, the last condition is that the limit when Z goes to infinity of Z times G of Z is equal to a constant. So you see, normally there's a bound to the spectrum, and if Z goes to infinity, you can neglect this. When Z is outside the region where this function is non-vanishing, and so this definitely goes like 1 over Z. But you see at infinity, this guy will not go to 1 over Z.
So when you say limit when Z goes to infinity, you mean the modulus of Z?
It doesn't matter. I mean, you have to be anywhere in the complex plane. I mean, yeah, the infinity is the same whether you're in the real or the imaginary direction. So you just go to infinity. But yeah, I mean, perhaps the best way to say it is to take the magnitude, but yeah, this is general. Okay, so that's the way to do it. So I know this is we are, doing very formal things right now, but for the rest of the week we will define quasi-particles in Fermi liquid theory. It becomes a little bit more physical, and we will start to study the Coulomb gas, which is sort of the key example that shows you the phenomenon of screening and introduces one of the important approximation, that's the random phase approximation. So that's the program for the week that I forgot to mention at the beginning. Okay. So if we have the translational invariance, let's start from G of R, R prime, and tau, which is equal to minus the time ordered product of psi R, R tau. For now, we dropped the spin index all the time, but we will put it back. Don't worry, R prime. Now, if we have a translational invariance, it means that we can do this. We can do 1 over volume of integral d cube r plus r prime over 2. So we integrate over the center of mass. And this is really unity, because we have translational invariance. This can depend only on r minus r prime. And then we do integral of d cube r minus r prime of this object, g of r, r prime tau. Then we use the change of basis. So psi of r is equal to sum. We have this mixed basis, sum over discrete white vector of r k times ck. Okay, so r. So that's just the change of basis formula. And this object in this funny basis, we said that this should be e to the I k dot r over square root of volume. So you do this replacement here. And then for this one, you do similar replacement. Psi dagger of r prime will be sum over k prime of e to the minus I k prime dot r prime times the c dagger of k prime. And then you write e to the I k dot r times e to the minus I k prime dot r prime as e to the I k plus k prime over 2 times r plus times e to the I okay. So what will happen is that when you do the integral, so if I didn't make a mistake, that should be equal to this. So if you do the integral over r plus r prime, this will give you a delta of k minus k prime. Okay. And then so you have k plus k prime now will become k times r minus r prime. So if you do okay, you will have just one sum over k. And then when you do this integral d cube r minus r prime, oops, I forgot here, e e to the I, oh, I used k and k prime already here. So e to the I don't know, q dot r minus r prime. Then you will select k here. You will select k equals q. So I won't go through this algebra and I just risk to make a mistake anyway. But you see the idea, right? Then the point is that this Fourier transform here of this g of r minus r prime will just be equal to this guy. Because I put q here, now this should be q. But that's it. Okay, so if I have translational invariance, I can always define the Fourier transform as a function of r minus r prime of this, and I get it in this form. That's all I wanted to say. Okay. Now, what happens if there are no interactions? If there are no interactions, so I write h minus mu n equals k equals sum over k of zeta k times c dagger k ck. So there are no interactions. So what is the time evolution of this quantity? So d ck d tau is equal to derivative of this. Okay, so that gives me the commutator of the k with the ck. And because k is time independent, this is the time independent because h commutes with k. K commutes with k, so I can evaluate this as an equal time commutator. And the number operator times ck gives me minus zeta k times the ck, which means that for tau larger than 0, gk of tau, so that would be this, okay, let me use a consistent notation. Gk of tau, so for tau larger than 0 is equal to minus exponential of minus zeta k tau times the expectation of ck c dagger k. Now, if I take this integral, then there are subtle points actually to play with this. But you see that it is going to look. I will let you go through this in the notes, but you see that it will have this structure: ikn minus zeta k, because I have ikn here. And I have zeta k here. Another way to see that this will be the g of k ikn is to remember that the spectral weight for non-interacting particle was a delta function. Okay. So if I replace this by a delta function, all I do is replace this omega prime by the zeta k. So in the case of the retarded function, I have omega plus iota. And otherwise I have this. So another way to do this is to remember that if I take the time derivative now of the time derivative of g of k tau, then I have a term that comes from derivatives of the theta function. So that gives me a minus delta of t. We looked at that the last time. And this, when the time derivative acts not on the time ordering operator, but on the c, that will give me minus zeta k times g of k tau. So the equation of motion is d tau minus zeta plus zeta k times g of k tau is equal to minus delta of tau. Now imagine that you do this integral. You integrate by part. That will give you a minus ikn, and there's this minus sign here. This will become a 1, and you end up with this. Okay, so that's another way to see it. Okay, last but are there any questions? Last but not least, we're going to look at the sum over Matsubara frequencies. Okay, so the first statement is that minus the integral over a contour that I will define in a moment of dz over 2 pi I times e to the minus z tau times e to the beta z plus 1 times 1 over z minus zeta k is equal to 1 over beta times the sum n equals minus infinity to infinity of e to the minus I kn tau divided by I k n minus zeta k. Okay, we will need to do this sum often because it will be useful to write Green's functions in this way with the IKN there. So, okay, so what have I done here? So I have defined this contour here. Okay, so this contour here is the sum over all these things. Okay, so what happens now when I do this contour integral around this, any one of these? Let's take one of them. Then I have to look at the whether this function is analytic or it has poles. Okay, well these things are on the real axis, so there's no pole along this contour here. But if I look at this function, so this function what does it look like in the vicinity of one of these poles? It looks like this: exponential of beta IKN plus delta z, where delta z is the distance here. So let me blow this up. So delta z is anywhere along this circle, plus 1. So we want these to become infinitesimal. We want to be as close as possible to this. So delta z goes to 0. So when delta z is small, then it means that I have 1 over e to the beta IKN is equal to minus 1, we said. So it's minus exponential of beta delta z plus 1. So when delta z goes to 0, it becomes small. Then this is just 1 over minus beta delta z. Okay. So the residue along this singularity here, the residue is equal to minus beta times 1, okay? So I replace z by IKN here, and z by IKN, and the residue is minus, that gets rid of this. And delta z is just because it's a simple pole. I'm using the residue theorem. Okay, and this is in trigonometric direction, so I get 2 pi I from this. So 2 pi I times the residue. So the 2 pi I disappear, the residue is 1 over minus beta, so the minus disappears, the beta is this. This becomes IKN because the residue is evaluated at this position, now IKN, okay? Now this is valid, I wrote this, but this is not general. This is just valid if tau is less than 0. Well, actually, it's valid in any case, but we will use it for tau less. What we're going to do now is valid only for tau less than 0. Okay. So if tau is less than 0, look at this this factor here. When z goes to infinity, then I have e to the minus beta z here, and beta is always larger than this. So for z goes to infinity, it goes like e to the minus beta z, and tau is negative, so that will give me a plus sign, but beta is always larger than this. So because of this factor, it will go to 0 when z goes to infinity. Well, the real part of z goes to infinity. And it's positive. So positive z. Now what happens if z is negative in this direction? So if z is negative, this disappears, right? But this here will make this term converge when z is negative in this direction. Okay, so this converges when.
What do you mean converge if z the real value of z is
I'm
equal
taking
to
z
0?
goes to infinity.
Yeah, so this goes to infinity.
No, because of this factor here.
Yeah, but in the numerator.
Yeah, but tau is always less than beta. Okay, so if I go in this direction, then this becomes e to the minus z tau minus beta z, and beta is always larger than tau in absolute value.
Yes, but for a real part less than 0.
So the other direction, this term becomes negligible when z is negative.
Yes.
But then this tau is less than 0. Okay,
No,
so
sorry.
minus tau is positive, and z goes in that direction. Okay.
Sorry.
No, it's not trivial. Okay, it's confusing. Okay, so everyone agrees that this sum here can be represented by this contour. And not only by this contour, but also in such a way that at infinity nothing happens. I mean that at infinity these functions are 0. So it means that I can do the following gymnastic. I will do a blow up. Sorry, I'm really getting later. So we have these functions, and we have this contour. Okay. Now, instead, what I can do is I can do this. So I have this. And I can do this. So this goes like this goes like that, this goes like that, okay? And then I can do this here. And then I have this, 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 this. Okay. Now, why is this equal to that? Tell me. Yes, Nicola. I don't hear you.
Yeah, because the limit's vanishing.
Yeah, if you take these infinitesimally close, then you go in the opposite direction, right? So these integrals, this part here is 0. And because the function is analytic there, now I can split this. Okay, I can take this and take it to infinity. And we saw that at infinity on this side, I will get a very nice 0 because the function is 0. But then assume that this pole here is on this side. Then when I take this to infinity, I have to so this is going up like that, so it goes like this. So I have to do this. Okay, so this is going up. This is going up, and I'm folding this, so it's going up. Yeah. So it means that this whole sum here can be transformed into this single pole. So I look at this function, and now I am taking into account this pole. And I'm going in counter, in the opposite anti-trigonometric direction. So the residue is minus 2 pi I. So this gets rid of the minus. So it means that this will be equal to e to the minus zeta k tau times sorry. No, this is correct. Okay, zeta k tau. And now this pole is has disappeared. I mean, that's the pole I'm looking at here. So it's this function here that needs to be evaluated at this pole. So I get e to the minus zeta k tau times exponential of beta zeta k plus 1. So that's the Fermi function, f of zeta k times the exponential of minus zeta k tau. Now, if you look at this definition here, when tau is goes to 0 minus, okay? So I'm going to 0 minus, it means that I need to take this order. Okay. So for tau equals 0 minus, g of k 0 minus is equal to the expectation of c dagger k ck. Okay. So when I replace tau by 0 minus, this becomes 1, and that becomes the Fermi function, and that's the Fermi function. Okay. And now you can work out that when tau is equal to, when tau is larger than 0, then you need to define the function differently if you want it to be able to converge everywhere at infinity. And then you will find that what you get if you look at, if you take the limit when tau is 0 plus, then this is minus ck c dagger k. So using the anti-commutation, this is minus 1 plus the Fermi function, f of z, okay? And if you look at the function that you need here to have everything converge at infinity when tau is positive, you will see that the function that you need is precisely the Fermi function minus 1. So everything will work out. Okay. Sorry for the being late. So I will turn off the recording.